Some words in mathematics are dangerous. In this video, the dangerous word is same. Because same sounds simple. Two things are the same if they look the same. The same size. The same shape. The same angles. The same distances. That is the ordinary expectation. But topology asks a stranger question. What if two objects look completely different, but mathematics decides they are the same? A circle and an ellipse are not the same in ordinary geometry. One is round. The other is stretched. Their curvatures are different. Their exact distances are different. Their measurements do not match. But topologically they are the same. One can be stretched into the other without tearing, cutting, or gluing. The exact shape changed, but the deeper structure did not. That is the beginning of topology, not geometry of measurement, geometry of survival. What survives when measurement is ignored? Classical geometry cared about length, angle, area, and curvature. Topology asks what remains when those are allowed to change. You may stretch. You may bend. You may twist. You may deform. But you may not cut. You may not tear. You may not glue separate parts together. Under those rules, a shape becomes flexible. And sameness becomes dangerous. The most famous example is a coffee cup and a donut. They do not look alike. One is a cup with a handle. The other is a ring of dough. But as idealized surfaces, each has one hole. If the material were perfectly flexible, the cup could be reshaped into the donut without cutting or gluing. This does not mean a real ceramic mug is physically a donut. It means that topology is ignoring thickness, size, angle, and material. It is keeping track of something else. The whole. In topology, the whole matters more than the exact outline. A sphere has no hole. A torus has one. No amount of stretching will turn a sphere into a torus without cutting or gluing. The difference is structural. This is why topology did not truly stop caring about shape. It stopped caring about exact shape. It began caring about deeper shape. The history of that shift begins earlier than the word topology itself. In 1736, Leonhard Euler studied the bridges of Königsberg. The city had landmasses connected by 7 bridges. The question was whether a person could walk across every bridge exactly once. At first, it sounded like a problem about a city. But Euler saw that distances did not matter. The width of the river did not matter. The length of the bridges did not matter. The exact shape of the land did not matter. Only connection mattered. Which landmass was connected to which? How many bridges touched each region? Euler reduced the city to a structure of points and connections. This was the birth of graph theory. But it was also an early sign of topology, a geometry where position and connection mattered more than measurement. Euler later discovered another clue. For many polyhedra, if E is the number of vertices, E is the number of edges, and F is the number of faces, then V minus E plus F equals 2. This formula was not about exact lengths. A cube and a tetrahedron look very different. But this count gives the same answer. Something numerical survives across many different shapes. This kind of surviving quantity is called an invariant. An invariant is something that does not change under the transformations you allow. In topology, invariants are the clues that tell us when two spaces are truly different. A shape may stretch. Edges may bend. Faces may distort. But certain features remain. Connectedness, number of holes, boundary, orientability, Euler characteristic, loop structure. Topology became the search for those features. In the 19th century, mathematicians began to see that the geometry of position was not a curiosity. It was a new language. Johann Benedict Listing used the word topology. August Mbius studied strange surfaces where inside and outside could behave unexpectedly. Riemann's work on surfaces showed that complex functions could create global geometric objects. The old idea of shape was expanding. Then Henri Poincaré gave topology a new force. In 1895, he published Analysis Situs. The title means analysis of position. Poincaré was not merely stretching rubber shapes. He was trying to build algebraic tools that could distinguish spaces. This was a major step toward algebraic topology. The idea was powerful. If a space is too hard to see, translate part of its structure into algebra. Study loops. Study holes. Study how paths can move. Attach algebraic objects to geometric spaces. Then use algebra to decide whether two spaces are different. This is one of the great turns in modern mathematics. Shape became something that could be measured without measurement. Consider loops on a surface. On a sphere, any loop can shrink down to a point. Imagine drawing a rubber band on the surface of a ball. No matter how it lies, you can slide it and tighten it until it becomes tiny. But on a torus, some loops cannot shrink. A loop around the hole gets trapped by the topology. It is not trapped by distance. It is not trapped by angle. It is trapped by structure. Poincaré understood that such loop behavior could reveal the nature of a space. The loop becomes a test. Can it shrink? Can it move? Can it pass through a hole? Can two loops be deformed into one another? This is why topology became so different from ordinary geometry. It did not ask, how long is this loop? It asked, can this loop be undone? That question opened a new world. It eventually led to the fundamental group, homology, manifolds, and some of the deepest problems in 20th century mathematics. The most famous of these is the Poincaré conjecture. In rough form, it asked whether a certain kind of three-dimensional space with the same basic loop behavior as a sphere must actually be a three-dimensional sphere. That problem would remain open for nearly a century. But this video is not about solving the Poincaré conjecture. It is about why such a question became possible. Topology had changed the meaning of recognition. To recognize a shape, you no longer had to compare outlines. You could compare invariants. You could ask what survives deformation. That is why topology became one of the languages of modern mathematics. It appears in geometry, in analysis, in dynamics, in algebra, in data, in physics, in the study of spaces too complicated to draw. When mathematicians cannot rely on exact measurements, they often ask topological questions first. Is this space connected? Does it have holes? Can a path be continuously moved? Does a loop shrink? What remains unchanged when everything flexible is allowed to flex? These questions are not weaker than geometry. They are different. Geometry says, measure the shape. Topology says, forget the measurements and ask what cannot be changed. That is the structure behind the theorem. Topology stopped caring about shape only in the ordinary sense. It stopped asking whether two objects look the same. It started asking whether one can become the other without breaking the rules of continuity. A circle and an ellipse are the same. A coffee cup and a donut are the same. A sphere and a torus are not the same. Not because of how they look, because of what survives. The dangerous word was same, because sameness is not absolute. It depends on what you choose to preserve. Euclidean geometry preserves distance and angle. Projective geometry preserves incidence. Topology preserves continuity. And when mathematics changed what it preserved, it discovered a new kind of shape. Not the shape of rigid objects. The shape of possibility. What can stretch? What can bend? What can move? And what can never be removed without cutting the space itself? That is why topology stopped caring about shape. Not because shape disappeared, but because mathematics learned to see a deeper one. For more stories behind the ideas that shaped mathematics, subscribe to Behind the Theorem.